This is a video presentation for a poster that I am presenting at the Midwest Dynamical System Conference. The topic of my poster is Bratteli Vershik models for substitutions on infinite alphabets. I want to thank the organizers for giving me this opportunity. This is an ongoing joint work with my two advisors, Sergey Bezuglyi and Jorgensen. In this poster, we will provide Bratteli Vershik models for a class of substitution dynamical systems on countable infinite alphabets. And this class is known as left determined, and I'll give a definition of left determined. We will provide two versions of Rocklin type lemma for these substitution systems. And using the Bratteli Vershik model that we have come up with, we will find explicit expressions for invariant and ergodic measures for the substitution dynamical system on countable infinite alphabets. And in the end, I will end with at least one example illustrating our work. So here is some background so this is simply the same as substitution system on finite alphabets. The only difference here is that, of course, I'm working with countable infinite alphabets. I'm working with bi-infinite sequence, and my subshift X sigma, this X sigma is no more compact. It's a Borel space. So that's the only big difference from the usual substitution systems on finite alphabet. We work with this left shift and everything else is the same. So X sigma is not a compact space. It is now a Borel space. Okay. So let me give the first definition, and the definition of left determined substitutions on countable infinite alphabets. And this definition is due to Ferenczi. He coined this term that a substitution is left determined if there exists an integer n such that any word in the language of length at least n can be uniquely decomposed, where each of these wi's are sigma ai's and ai's are unique. So let me just write this down. W is W1, W2, Ws minus 1, Ws. So all these W2 to Wsi's are just sigma of Asi minus 1. This is sigma of A2. But W1 can be the suffix of sigma A1, and Ws may be a prefix of sigma As. And if we can write every word like this, if we have this unique decomposition, then we call our substitution to be left determined. And he gave an example in his paper, the squared Drunckenmans substitution. He proved that it is a left determined substitution. Now I give the definition of Borel-Bratteli diagram. So first, a Bratteli diagram is a graded graph where we have the vertices are graded, and it's easier to just show you an example. So here is an example of a non-simple finite rank Bratteli diagram. And I'm not going to go in what is non-simple and finite rank. So here are my vertices, V0, the level of vertices, V2, V3, and so forth. And this is edges E1, E2. My Borel-Bratteli diagram is similar to this Bratteli diagram. The only difference is that at every level, I can have countably many vertices instead of finite as shown in this diagram. And then my edges would also be countable infinity. Okay. Now I denote by YB the infinite path space of this diagram. And I can put an order on my Bratteli diagram, and I'm not going to go in detail of that. And on this infinite path space, we work with this Vershik map, which is, I have given the definition here, but that's just the tail equivalence relation. Okay. Now we are ready to give the first theorems, and these are Rocklin lemma type theorem. So I will denote by this a cylinder set of length n. And I'm saying, my first theorem is saying that if sigma is a left determinant substitution on countable infinite alphabet A, and x sigma t is the corresponding subshift, then I can write the space x sigma as disjoint union O, and this is words of length s, disjoint union over the cylinder sets of this form. Actually, these are T towers with the base is of this form. So disjoint union of the T towers where base are cylinder sets of this form. Okay. The second theorem says that if I assume that my sigma is bounded length, so it is still left determined on countable infinite alphabet, but in excess, if I assume that my sigma is of bounded length, then I have one more expression of x sigma. And here, the base of my towers are of this form coming out of the powers of sigma. Okay? So I have two Rocklin lemmas for substitution on infinite alphabets, which are left determined. So using this theorem, using theorem 2, so as soon as we have nested sequence of Kakutani-Rocklin towers, we can construct Bratteli Vershik models, and that's what we did. We construct, if sigma is a left determined bounded length substitution on an infinite alphabet, and x sigma t is the corresponding subshift, then there exists a stationary, it is important to know that it's a stationary, we construct the stationary ordered Borel-Bratteli diagrams such that x sigma t is isomorphic to Vershik map on the path space of P. Okay? So this is Bratteli Vershik model for substitutions on infinite alphabet. And using this model, once we had this model, we used it to find expressions for invariant probability measures. So let me just read this theorem. If sigma is a bounded length left determinant substitution on Z, and I'm writing Z in terms of Z because it's easier to write this theorem. You can have it on any infinite alphabet, such that the substitution matrix is irreducible, aperiodic, positive recurrent, with constant row sum. It looks like I'm putting a lot of restrictions, but it's not. These are not very hard to find restrictions. Then there exists a T invariant probability measure. So this constant row sum was to get probability measures, which is given by this expression. So here, this is a cylinder set of length n, and it is ending with this integer j because I'm working with Z, and Lj is the jth entry in the parent Frobenius eigenvector of F. Okay? And lambda is the parent Frobenius eigenvalue of F. So I get an expression for my T invariant probability measure. Furthermore, I'm saying if my sigma is of finite size, and what do I mean by finite size? Finite size means that if I apply sigma to a word n, then it does not go off. For example, in this example, when I'm applying sigma to 4, then I'm getting, when I'm applying sigma to 0, then I'm getting -1, 0, and 1. I'm not getting like -1 million. So it's not going off to infinity on it. It's not just blowing up. And that's what I call my sigma to be finite size. So if my sigma is of finite size, then this expression that we have found is actually ergodic. So this invariant measure that we have found is ergodic. And these are our two theorems. And here is one example, and this is one step back, two step forward substitution on Z. And I've written it explicitly here. And here I've given two levels of the Borel, because this is a stationary diagram, so just giving two levels will work. So I have given two levels of the corresponding Borel-Bratteli diagram. And thank you for your time. Thank you.